Good morning, good afternoon, good evening. This is Pradeep Dubey, Intel Senior Fellow, also Director of Parallel Computing Lab. Thank you for the warm introduction. And we are entering a new era in computing, and it has significant implications on both how we do computing and what computing can do for us. We have been so far machines and us humans have had a nice division of labor. Machines have been crunching numbers, and we humans are highly valued for our experience with decision making. So even the simplest of simple decisions generally is made by some human somewhere, and machines, and pretty much even the simplest of simple number crunching is not done by humans, even when they're capable of it's done by machines. This division of labor is what is changing or getting disrupted rather by AI. And AI is now machines are actually claiming that they can do not just number crunching but better decision making as well. And to the extent this is true, or wherever this is true, or whenever this is true, this has significant implications on many things, not just how we do computing, but what computing can do for us in a large sector of society, in a large class of applications where so far computing had very little impact. And they were all human decision making, human services dominated. Now they are getting disrupted, now they're changing. And it's not that far-fetched to say that pretty soon we will be entering an era. We can now see that we will be entering an era where machines will make more decisions than human. And that will be quite a milestone. And let's understand why and where it's happening, and the underneath what's driving it. The science of it, quote unquote, has been known for quite some time. But there's a reason why it never happens for such a long time. Meaning, we know that for a very small number of problems, small set of problems, we can actually solve them, quote unquote, from first principles. Meaning, we have a deep enough understanding that it's down to some analytical models where we can throw a lot of compute and we can begin to solve through those first principles. But for a large number of problems, for 99+% of the problems in the world, we don't have anywhere near such deep understanding. There is no Newton's law, there is no Navier-Stokes type formulation. So all we have to do is start from observations, right? Input-output observations. You have tons of data of such behavioral data, input output data, and we have to figure out, reverse engineer the black box with that data. And this is where deep learning, or machine learning rather, comes in. Now, so far we never had enough data to be able to reverse engineer good enough models. The test of the model goodness is whether it can really predict, make good enough predictions aligned with real world. This is what is changing now. Now what's making AI very effective is this ability for machines to make learn good enough models. And this is wherever this is and whenever this is true, as I said, that this has significant impact. And what makes AI effective in practice is whenever we have at least a model structure that we are trying to train, and that model structure, if it matches what you're trying to learn, the objective function that you have, that quote unquote inductive bias, implicit or explicit, when we have a good enough a good set of inductive bias, we are able to effectively learn through large enough data, but their learning is much more efficient. The other thing that makes learning or training much more efficient is how well we manage exploitation versus exploration, right? And if we can avoid, quote unquote, as you see in this picture, the sharp minima, and stay and find these methods which take us to a generalizable, flatter minima, where we not only, because remember, we are trying to not find a specific a person or a specific target, but we're trying to look for similar things, because the real world will not give us exactly what we were trained on. It will be similar. So that ability to generalize from the training data is super important. And that's the very big challenge in AI. And whenever we are able to do this, whenever we are able to learn this fast changing enough function properly, we have, with the learning, the training is very effective, and we see that in its predictive power. Now, that predictive power that we just talked about is actually showing results, and some pretty surprising results, right? That even in deep science areas, we are not simply the approach that we have had so far, the one I showed on the left side, the first principle based methods or traditional approaches, they are getting outperformed whenever we are able to apply with enough data deep learning methods, which somehow, right, are able to find get to the optimum, right? And again, like I said, generalizable optimum much faster, much better. And when it happens, right, the speed ups are pretty impressive. Here I'm showing you one of our recent results, and and this work was done with lead scientists at Tata Institute of Fundamental Research, right, right, and they're in India, plus along with other researchers in the field of physics, as more specifically astronomy at NYU, Abu Dhabi, and Japan. And you can see the work that we did with them, that we are now that we are able to extract these seismic parameters, right, from data coming from Kepler and TESS space missions. These are huge amount of large data sets, right? And the goal here is to find somehow be able to learn parameters that govern the stellar evolution of red giant stars. Now, what's fascinating here is the speed with which we are now able to do on Xeon Platinum platform, Intel-based platform. Our ability now to actually do these things that we earlier did through prior methods, now we're seeing 10,000x speed up, right? And you can try, and you see the performance that we are getting is enabling us to do science, right, much faster. That iteration that we can now do now, when we can actually learn these, extract these parameters for thousands of spectra in under 10 seconds, many times faster than what we did before, using these new deep learning based methods, where we have a deep learning systems with X number of 1D convolution layers, to be specific, 6 1D convolution layers followed by 2 LSTM layers and a dense layer. And training that network with the data that we collected, right, we are able to, as I said, that we are able to learn these parameters good enough that we can now actually see predictions, accurate enough predictions, right? And accuracy is judged again by the precision recall of this prediction of this learned model, which is precision of 87% and recall of 86%. Pretty good, right? We're able to have such high quality models, and not just high quality models, but look at the inferencing speed of these models, right? It's much faster. Now, this ability to learn these parameters from data is what is not just limited to scientific data, but any place where we have data. And hence you can begin to see that where else do we have such this large amount of data? Not necessarily in the space, but also right here around us, right? And that data is the data of quote unquote health data, biology data, right? This immense amount of data. And it's again one of those fields that is ripe for such disruption, because pretty much our understanding of biological phenomena is quote unquote quite poor, right? We very rarely understand enough at an analytical level, probably almost in no cases, right? So it's pretty much the only hope here is to really learn through large amount of data, and we are getting data in every form, as you can imagine in these days in biology, because of the data has been digitized and sequences have improved significantly. So digital data in biology is growing at a pace never seen before, and hence biology is experiencing what we call an AI moment, which you can clearly see in as research papers like the one that we are just plotting here, that are just in the last few years, right, 21,000 papers since 2020 alone, right? This is greater than 50% year over year since 2019, and you can. This is why we call it biology experiencing a quote unquote AI moment. Now, it's not just and in these papers, but you can also see the output of methods like AlphaFold, right? We are now able to after decades of work, we only knew structures of, let's say, about 4,000 proteins, right? And now with the help of AlphaFold, 20,000 human protein structures have been decoded, right? Now, this is the power of biology getting AI-fied, or what we are calling here that quote unquote AI is eating biology. The speed that it has offered it's put it in high gear, and biological data set is going to be largest data set on the planet. It dwarfs every data set that we have seen today. So far, at this point today, the largest data set that we see is video data set, quote unquote, YouTube data sets, right? But the biological data set will dwarf all of this, the data set of today. Why? Because of simple reason, right? We just imagine a single human genome is about half a terabyte of data, but that we so far thought that that genome sequencing is all we had to do to understand the phenomena that we go through, right? But not just our own genome, but the microbiome genomes, which are million genes, right? They have more effect on our body, on our body's functioning than our own genomes, right? So therefore, we need to sequence not just our own genome, but we need to be constantly sequencing our microbiome, right? Which is constantly evolving. And this is at the amount of digital data and processing that you need is immense. But the exciting thing is it's actually possible now. And that's what is causing excitement, that we can actually go all the way from algorithmic computational management, and the data management requirements are immense. And you see here we have at a high level, we seeing that this is leading to compute growth demand huge, 10,000x, and it's primarily again driven by the fact that we have huge amount of data to process. So there's a significant data management component here, data storage, data management component, and of course then comes the processing part, the algorithms like the deep learning inspired or other machine learning algorithms. So it's both, and they need to happen real time so that we can actually see some of these effects and real time and be able to take decisions real time. So it's at the heart of any large data. When data grows, almost invariably the dimensionality grows, and that's called cursor dimensionality. And when dimensionality grows, the only way we know how to represent high dimensional data is non-Euclidean data, is graphs. And graphs is where we have to therefore be very efficient in processing graph data sets and quote unquote graph neural networks, because the effectiveness of graph neural networks is phenomenal in terms of actually dynamic graphs, because so far we were able to really run good graph algorithms, but pretty much on static graphs. But that's not what we're talking here. We're talking dynamic graphs, and not just in social networks, but also inside our body, right? The metabolic pathways and so on. So when you are dealing with dynamic graphs, accelerating dynamic graphs, and being able to deal with dynamic graphs, we have again the algorithmic breakthrough through graph neural networks that actually lets us effectively look for learn your communities and detect communities and such problems in a large enough graph data sets. And this speeding it up is not trivial. Why? Because it doesn't have the same compute density or intensity of convolutional neural networks, right? Because so you have to sampling that large graph and is immensely hard because of the memory irregularity that it creates. So as you can see, that this work that we just published, where we're doing full batch training, we're not sampling, we're doing full batch training, and that full batch training is we have sped it up almost fourfold on a single socket Xeon Cascade Lake. And not just that, we also have managed to scale it all the way to 120 hundreds of nodes. And you can see the scaling is pretty good with the bounds that we had, analytical bounds. We are pretty much in there with a very decent scaling for the most popular graph library called DGL library, right? And hence you see the performance that we've achieved here is quite impressive. Now this is the compute part of it, right? Now it's now giving us it's helping us signing up for these very hard problems in molecular search, right, which is at the heart of drug discovery. And we have actually we are collaborating with probably world's greatest thought leaders in AI, Professor Yoshua Bengio and his and the Institute Mila in Canada. And the goal here is to figure out how we can actually cut down the search space or traverse the search space, which is hugely much bigger than our entire internet search today. The entire internet search is only, let's say, roughly 10⁹ web pages. Here we are dealing with complexity which is much more than that, and so far we could only do this through, like I said, first principles simulations. And that those simulations are pretty slow, and with even the amount of compute power we have, we could only do something like a 10⁹ molecule types complexity. That's the only compute bond that we had so far. Now we have an ability to go almost and 10⁹ more, 10⁸ molecules. That's the goal for this project called Lambda Zero, and that we can actually search that much space. Now, remember, it doesn't stop there. If we had zeta scale, we could go another 1000x or more. So it's a pretty, now when we have that ability to search, we can this large molecular space, our ability to find and personalize drug discovery, it grows immensely. Okay, and you are now able to find precisely the most effective molecules. At least you're able to cut down the search space so much that you can then do lab experiments with highly likely successful candidates. And this is again the not just the compute part of it, but like I said, that there's also a data part, because the data is massive. So you have to constantly look for and make sure that your data management is under control. And in here, again, we have very exciting result thanks to AI, because this BOW is work that we did where we are using AI's help in making sure that the end-to-end query optimization is better than the best methods we have. And what's the check here? The check is simply that you have to touch minimal amount of data, quote unquote cardinality, right? You're reducing the cardinality of the data that you touch, and so that your query is processed at the fastest speed. So BOW is showing how we can actually do end-to-end query optimization for data, for data management. And the learned methods that we have now here are beating human engineered methods for these query optimizations of decades. So as you can see some results here, this work got us Best Paper Award in the Data Management Premier Conference, SIGMOD. And what you see here, this work done with Professor Tim Kraska, who is a pioneer of these learned methods at MIT, that we can, as you clearly see here, that it's beating commercial SQL servers, right, DB2, and it's beating them on real data sets. It's able to outperform them all in terms of, and remember, it's entirely machine learned. So there are no, so these, and again, the key here was to be able to train a structure which closely aligns with the structure you're trying to learn. You're trying to learn a query plan, right? That's why we had to come with a tree convolution networks, TCNN, and train that with data. Good, and the training became, of course, it's effective enough that's actually beating decades of old query engines. So this ability to process, manage data, minimize data accesses, have amazing efficient data management, combined with AI methods, which have first is a sparse component to it, so they can deal with highly sparse graph data sets. And then, of course, the deep learning, the dense data sets, it's an easiest problem. So from data management to sparse data management to sparse learning to dense learning is the pipeline that we have finally managed to put together, and we are seeing results. If you see here the same, this is again BWM methods, which is used for generally for when you have a reference sequence and you're trying to match it to a read, and generally large, reasonably large read, more than 70 base pair. This is the most common method used. And as you can see, we are working with again the thought leaders, right? Dr. Heng Li, right? We have who's the author of BWMM. We have actually managed to improve this method very, very significantly. And you can see here on a two-socket ice lake, it's higher is better. Our throughput is better than anything comparable, right? Again, we typically think that the CPU is not good enough for this perception that CPU is somehow not good enough for deep learning machine learning. Not true. You can clearly see here that a CPU platform, right, commonly available, so it's everywhere in the data center, is actually outperforming the best machine, the best that any machine can do, and by a significant margin. And the result is again very simple, that this is why it has a huge amount of downloads, and it's enabling communities, and you can see some examples here of research, including it was used for the figuring out the COVID-2 transmission. Okay, so the impact on society is pretty clear. And moving on, another method, right, M2 fast, which minimap 2, again on our vanilla Xeon, this method has been sped up by more than 3x. And again, as you can see here, multiple data sets, and we are showing here how we have managed to improve this method from the best that we have. But again, this also a collaboration with Dr. Hengley. And moving on, this single cell sequencing ATAC sequence data right here, which is a very hard problem, right? And we are working with leaders in the field, and this is a work that we have just published, right? And you can see the links here, and you can see how we started from and the baseline of 1, and that number has gone almost close to 9x better, right? And on a 16 sockets Cooper Lake. Now, and this is with optimizations that we have managed to put in here. This is 2.3x speed up over the popularly used NVIDIA Clara Parabricks on a DGX1 box, and here we are using vanilla CPU, right? Of course, 16 sockets of Cooper Lake, right? And somewhat older CPU, by the way, right? And we have 1.8x speed up for over 16 sockets of Ice Lake, right? Over NVIDIA with using 16 sockets of Ice Lake. So you can clearly see that the performance is pretty impressive. And again, remember, these are uglier problems. These are not your simple and deep learning problem, dense problem where you can just apply a tensor core and flops is the only thing that matters. These are uglier problems. The problems for such as this, the compute is not the only problem. Compute is not often the problem. It's the feed part. It's the irregular compute part, which is the challenge. And therefore, the efficiency of compute for irregular computation matters more than simply raw peak flops. And you can clearly see that these machines are not higher peak flop, but they have the higher efficiency for such irregular processing is the reason why it's outperforming everything else. So moving on, we are further looking at these end-to-end problems, and in the context of health data, where the biggest issue, like I said, that even when we know that we do have a large amount of data, because it's health data, you have to understand that there's privacy concern, right? And so here we have come with, again, working with leaders in the field, right, in this, we have come up with a plan which actually kills two birds with one stone. Not only we need large amount of data, we have to privacy preserve it, right? And even if we didn't have privacy concerns, sending so much data to a centralized place is also very expensive. So what we're doing here is we're solving both problems. We are privacy preserving the data, and we're doing it only locally. So we never send the data, but we only send model deltas so that a model is being learned at centrally, but data is never sent centrally. It stays local. And that is what we call, that's federated learning. Technique of federated learning is what we're showing here is now effectively being deployed. And this is our work with UPenn, right? Another thought leader in this field. And this is, you can see it was published in Nature. This work, as you can clearly see that you're now able to do much better training with full data. And earlier you could not do it for these reasons we just mentioned. And the net is that's much better. It's much better than what these institutions could do when they were not able to train on full data. And now they're able to privacy preserve and still train on full data. Again, all such stuff, our goal is to make it available to the community so that the researchers out there, the community benefits. And that's what we have done. This entire thing has been open source, and it's called OpenFL, Open Federated Learning, and it's available through the links that you see here, and it has all this the quote unquote goodness features that I just talked about: privacy preserving, and attestation integrity, federation deployment, and software stack that does it, plus your data curation that needs to happen, all using the popular TensorFlow, PyTorch, Keras frameworks. So, and this is available, and again, it does benefit from and does build or leverage Intel SGX for delivering this capability. So, if we now continue. As you can see that I'm trying to just make sure that we summarize the essentials here, that we have gone from the observation that huge amount of data, if we properly find leverage a structured, we can learn highly complex structure, right, of this data, if we have enough data and efficient enough training algorithms. And it's not just true for it's true for science or physics in general, but it's especially true and effective for biological data also. Of course, the challenge with biological data and machine learning is that we have to take care of everything you see here listed: privacy, the volume of data, the agility and the dynamicness of data. And when we are able to deal with data management problem as well as compute problem in an efficient manner, the speed ups that we are seeing, the performance gains that we are seeing, the efficiency that we are seeing is pretty impressive on machines that we have. And we're of course not stopping with the machines we have. Our goal is to actually help us. Our goal is to actually learn how to design such machines better for such computational needs. So starting with these applications, going down to the software that we are actually crowdsourcing, deploying so that we can learn better. Ultimate goal is to come down and design machines for AI better. As I started my talk by saying that AI is fundamentally changing not just what compute can do for us, but how we do computing. So we are trying to learn all this to actually finally design machines differently, machines better. And to make that happen is again not just us, but we are enabling industry of computer architects in academia, anywhere, wherever they may be, so that machines get designed better. And that effort is what you see here reflected in our collaboration with the University of Michigan. And we have open sourced, and we're creating this genomics bench, where we have captured the motifs, the essentials of such compute processing in these 12 representative kernels that you see listed here. And we are optimizing them, of course, for the silicon that we build. We're redesigning features in our silicon so that these kernels, these motifs perform the best. And not just limiting it also, it's also out there as Transomics acceleration library for anyone to design anything, meaning it doesn't have to be it can also be a special purpose processor, right? Accelerator of some kind, or any other machine, but the primitives are being open source so that we can all together make these primitives become better. And if we make the primitives better, of course, the rest of the pipeline of compute and data processing will improve as well. And so this is pretty much all I had. And I'm happy to, I look forward to the discussion that follows this, and any other questions that you may have. Thank you.